In this video, we're going to go through question 11 from the NESA Sample HSC Mathematics Extension 2 exam. So part A, let z equal the square root of 3 minus I. And the first part is to express z in mod arg form, modulus argument form. So we've got z is the square root of 3 minus I. To get mod arg form, we need to work out the modulus and we need to work out the argument. So let's do the modulus first. The modulus of z is going to be the real part squared plus the imaginary part squared. Now the imaginary part here is -1. It's not -I. It's the coefficient of I, which is the imaginary part. So -1 squared, and then we have to take the square root of that. This will be the square root of 3 plus 1, which is the square root of 4, which is 2. So our modulus, the mod of z, is equal to 2. To work out the argument, whenever I want to work out an argument of a complex number, I always like to have a really quick idea of where I'm sitting in the complex plane. So this is saying that I go across root 3 units, go across root 3 units and then down 1 unit. So I'm sitting somewhere in the fourth quadrant, and I'm actually going to indicate that like this. Okay, so this is the point root 3 and this is the point minus I. Now the reason I do that is because when I work out my modulus, I know that it's not going to be, or it's going to be something in the fourth quadrant. So I always start off by just working out what it would be if it was sitting in the first quadrant. So that means with both of these being positive. So I would start off by doing tan inverse of +1 over root 3. And that is, of course, going to be 30 degrees or pi on 6 radians. Okay, so when I work out my argument, my arg of z, really what I'm doing, since I know I'm in the fourth quadrant, it's going to be minus basically this working out here. It's negative of that working out. So minus tan inverse 1 on root 3, which is minus pi on 6. So if I want to write this in mod arg form, I can say z is equal to 2 cos plus I sine. We're going to just abbreviate that as cis minus pi on 6. And that is our final answer there. Now part 2 says to show that to show that z to the 6 is real. Okay, so we just want to compute z to the power 6. Let's move this up a little. So really what we're doing, I think it's a bit standard. We're just going to be applying de Moivre's theorem here. So with de Moivre's theorem, the modulus gets raised to this power, so that'll be 2 to the power 6, and the argument gets multiplied by the power. So this will be cis of minus pi on 6 times 6, and it's a good idea to indicate that we've used de Moivre's theorem. So by de Moivre's theorem. Okay, so we have 2 to the 6 times cis of minus pi. Now, what is cis of minus pi? Well, if we quickly draw up another axis here, minus pi means that we're starting here and we're going all the way across in the negative direction by pi radians. So we're doing a half circle, a semicircle, and we end up landing here, which would be -1. So this is really minus 2 to the power 6, and 2 to the power 6 is 64. So this is minus 64. And that is purely real. Okay, so we've shown that z to the power 6 is purely real. And then part 3 says to show that, to find a positive integer n such that z to the n is purely imaginary. So we want to have a look at what z to the n is. Z to the n. Well, again, we're going to pretty much do the same thing that we did above. We're going to use de Moivre's theorem here by raising this complex number z to the power n. Again, by de Moivre's theorem, this gets raised to the power of n. So we have 2 to the n. And our argument gets multiplied by n. So this is going to be cis minus pi on 6 times n. Now we want this to be purely imaginary. Now what does it mean for a complex number to be purely imaginary? Well, if we have a look at our argand diagram here, it means it's lying on the imaginary axis. Okay, so if it's lying on the imaginary axis, that means it has an argument of either positive pi on 2 or it has an argument of negative pi on 2. Or if you like, it has an argument of 3 pi on 2. If you wanted to use that as well, that would work just as fine. So maybe we should indicate that in our answer here. We would say z to the n is purely imaginary if and only if the argument of z to the n is equal to plus or minus pi on 2. Now the question here says find a positive integer. That just means give us one positive value of n, which would give us a purely imaginary number. Not a problem. All we have to do is we have to set this thing here equal to plus or minus pi on 2, and that'll give us 1. So minus pi on 6 times n equals plus or minus pi on 2. Now you can see that we're not going to look for the positive pi on 2 case. We don't want positive pi on 2 because that would require a negative n value. Okay, so we'd have to actually look for minus pi on 2. So if we just rearrange this to solve for n, this would give us, we can cancel off our pi's. This would give us plus or minus 3. But of course we want n to be positive, so therefore n equals 3 gives a purely imaginary value for z to the n. And that's the end of part A. Okay, question B. Part I says to show that 1 minus 2i all squared equals minus 3 minus 4i. So basically what we're going to do, we're going to start with the left-hand side and just do the expansion and show that it's equal to the right-hand side. So the left-hand side is 1 minus 2i all squared. This is a perfect square, so we expand it in the normal way. It's the first term squared minus 2 times the first times the second, plus the second term all squared. So we've got 1 minus 2 times 1 times 2 is 4, so 4i, plus 4i squared. Of course, I squared is minus 1, so this is 1 minus 4i minus 4, which is minus 3 minus 4i. You don't really need to put in all these steps, but I'm just doing it here. Okay, and this is equal to the right-hand side. Excellent, so we've shown the first bit. And then the second part says, hence solve the equation, z squared minus 5z plus 7 plus I equals 0. So let's write that equation down here. We've got z squared minus 5z plus 7 plus I. Now, it's not going to be terribly easy to factorize something like this, so looks like we're just going to resort to the quadratic formula. Okay, so z is equal to minus b, which is minus negative 5, plus or minus the square root of b squared, so minus 5 squared, minus 4 times a, which is 1, times c, which is 7 plus I. So it's the square root of all of this. And we divide that by 2a, so 2 times 1. Now we have minus minus 5, which is positive 5, plus or minus. Underneath the square root, we have 25. And then we have negative 4 times 1, which is 4. And then that's 4 times 7 gives us the negative 28. And then the negative 4 times I gives us negative 4i. And then we want to take the square root of that, all divided by 2 times 1, which is 2. If we continue simplifying what's underneath our square root, 25 minus 28 is minus 3, and then we have the minus 4i. And we notice that the thing that's underneath our square root is actually something that popped up in the first part, in part I. So I'm just going to rewrite what we got from part I. We saw that it was 1 minus 2i. iPad's playing up a little bit. We saw that it was 1 minus 2i, all squared, equals minus 3 minus 4i. But now what we want to do is we want to take the square root of minus 3 minus 4i. So we take the square root of both sides here. So here I have the square root of this, and that would be equal to plus or minus the square and the square root will cancel, and we get 1 minus 2i. Okay, so we can now use this in our working out here with the quadratic formula. So we have 5 plus or minus 1 minus 2i, or divided by 2. And so we have two cases. The case where it's positive, where we're taking the positive here, and the case where we're taking the negative. So in the first case where it's positive, we have 5 plus 1, which is 6 minus 2i, all over 2. And our other answer would be 5 minus 1, so 4, minus 2i, which would be plus 2i over 2. And then this simplifies to 3 minus I and 2 plus I. And these are our two answers for z. We've solved our quadratic equation. Now, probably at this point, it would have been a good idea to say from part I, just to indicate that we're using that result that we've already worked out. But that's the end of question B. Question C. Part 1 says, find numbers a, b, and c such that x squared plus 8x plus 11 over x minus 3 x squared plus 2 equals a over x minus 3 plus bx plus c over x squared plus 2. So really what we want to do is we want to do a partial fraction decomposition here. So our first step is to write the right-hand side as some fraction, just one fraction. Essentially, we want to add up our two fractions. And in doing that, our numerator would look like this. A times x squared plus 2 plus bx plus c times x minus 3. And then all of this is being divided by our common denominator, which is x minus 3 x squared plus 2. Okay, so that means that this fraction here is now equal to this fraction here. And since their denominators are the same, well then their numerators must be identical. So we can say that x squared plus 8x plus 11 is identical to a times x squared plus 2 plus bx plus c times x minus 3. And now what we want to do is we want to try to find these three values for these three numbers, a, b, and c. So probably the first one to start off with, or the easiest one to find to begin with will be a. And the way we'll do that is we'll let x equal 3. And you can see that when we let x equal to 3, this term here becomes 0. And so this whole term just disappears, becomes 0. So if I let x equal 3 on the left-hand side, I'll have 3 squared, which is 9, plus 8 times 3, which is 24, plus 11, equals a times 9 plus 2. So, okay, what do we have on the left-hand side? 9 plus 11 is 20, plus 24 is 44. And here we have 11a. And so therefore a is equal to 4. So we found our first value for a. One of the letters, it was a is equal to 4. Now we try to find b and c. And I think the best way to go about this, there's not really a nice value we can substitute in which would make this term become 0, unless we want to delve into the complex world, but it's not really nice to do that. So probably what we'd do is we would look at comparing coefficients on the left-hand side and the right-hand side. So if we have a look at the coefficient of x squared, what's the coefficient of x squared on the left-hand side? Well, that's the only x squared term, and the coefficient is 1. On the right-hand side, we have an x squared here, so the coefficient of that is a, and we just worked out what a was, that was equal to 4. But we also can get an x squared term by bx times x. That would give us bx squared, so the coefficient there is a b. If we rearrange for b, we get b equals 1 minus a, but remember we just worked out a to be equal to 4, so this is 1 minus 4, which is equal to minus 3. So there's our value for b. Let's highlight that one as well, because that's part of our answer. And then finally, we need to work out a value, or we need to find a way to work out c. And probably I would look at the constant term, or really this is the coefficient of x to the power 0. So we want to have a look at, can't spell, the coefficient of x to the power 0, which is the constant term. On the left-hand side, the constant term is 11. And on the right-hand side, the constant term comes from a times 2, so that would give us 2a. And from c times negative 3, so we have minus 3c. If we rearrange, we get 3c equals 2a, but remember a is 4, so 2 times 4, which is 8, minus 11. The right-hand side is negative 3, and so c would be equal to negative 1 once we divide through by 3. And so this here is our final part for part I. So a is 4, b is minus 3, and c is negative 1. Now part 2 says, hence evaluate the integral of x squared plus 8x plus 11 over x minus 3 x squared plus 2. So clearly, we need to use our partial fraction decomposition to help us integrate this integral. We want to rewrite our integrand, the thing being integrated, in a different form, which is using what we've done just above. So we want to write our integral as a over x minus 3. Now we said a was equal to 4, so this will be 4 over x minus 3, plus bx plus c over x squared plus 2. Now b was negative 3, so minus 3x, plus c is negative 1, divided by x squared plus 2 dx. Okay, so now we want to try to integrate this, and this is a little bit easier to deal with. So the first part here, this one is pretty standard. It's already a log function. It's already written as something we can straight integrate as a log. So this will be 4 log of the denominator. Now for the next bit, I'm going to split it up in a certain way. But before I do that, let's just write it so that we can see exactly what we're doing. We'll take it one step at a time. Okay, so we still have our 4 log. Oh, that looks like a h. 4 log x minus 3. And now I want to split up my numerator. So I'm going to write this as minus 3, the integral of x over x squared plus 2 dx, minus the integral of 1 over x squared plus 2 dx. Now with my first integral that I've got here, with this bit here, I can see that this is almost in the form of a log. All I'm missing is a factor of 2 on top. So I can add that in, I can multiply by 2, but of course I need to divide by 2 as well to compensate for that. So overall I haven't changed anything, but now I can see that this is in the form of a log. So I'll be able to integrate that. For my second integral, this one here, this looks like a tan inverse, okay, where in this case our a is going to be the square root of 2. So I might just write that under here. A looks like it's going to be the square root of 2, because I can write 2 as the square root of 2 squared. So we can now go ahead and do our integrals. So this is 4 log x minus 3. Here I have minus 3 halves, log of the denominator, so log of x squared plus 2, minus, now be careful because with a tan inverse, you have to multiply by 1 over a outside of the tan inverse. So this is 1 over root 2, tan inverse of x divided by a, x divided by root 2, and of course we add a plus c because we have no more constants, no more integrals left over. And that is our final answer. Part D. Using the substitution u squared equals 4 minus x squared, or otherwise, evaluate the integral from 0 to 2 of x cubed times the square root of 4 minus x squared dx. Now here they've given us a substitution to use, but they also have said or otherwise. So we might use a method if that's something that we want to do. I suppose another substitution you could make would be some sort of trig substitution. Looks like x equals 2 sine theta might work. But I think since they've given us a substitution to make, let's just use that substitution. Okay, so we know that when we have a substitution, we need to differentiate it. So let's differentiate this. So to differentiate this will be 2u du on dx times minus 2x, that's just by the chain rule. And we want to get dx kind of by itself. So we can cancel off these 2. So I'll multiply by negative 1 on both sides. So I'll get minus u du equals x dx. And I'm going to leave it as x dx, because I can see that I can pull out one of these x's and join it up with that dx in order to get the x dx that I have here. But I also need to change my limits of integration. So when x is equal to 0, u, or u squared rather, is going to be 4 minus 0, and so u is going to be equal to 2. When x is equal to 2, u squared is going to be equal to 0, and so u is going to be 0. So now we can go ahead and make our substitution. Before we do that though, just as I said before, I'm going to write this x, take one of these x factors out and put it next to this dx, just so I can make it very clear of what I'm substituting and where everything's going. So this is the integral from 0 to 2 of x squared. We're taking one of the x's out. Square root of 4 minus x squared times x dx. Okay, I really wanted to write that x dx by itself so that I can clearly see that's what where I'm substituting this part in for. Okay, let's change our limits. So 0 became 2 and 2 became 0. Now this x squared bit, that's going to come from up here. We can rewrite this as x squared equals 4 minus u squared. So we want to substitute that in for our x squared. So we have 4 minus u squared. The square root of 4 minus x squared, so this becomes the square root of u squared, times x dx. Well, what's x dx? That's minus u du. So this is multiplied by minus u du. This minus sign here, it has the effect of swapping these limits. So that gets absorbed into our integral and we swap our limits. And then we have 4 minus u squared. This is a u, and here we have a u, so we're multiplying by u times u, which is u squared. Integral from 0 to 2 of 4u squared minus u to the power 4 du. And now this is fairly basic. This is 4u cubed on 3 minus u to the 5 on 5. Substitute in 0 and 2. All those are our limits. Now we sub them in. Okay, so when I sub in 2, what am I going to get? I'm going to get 32 on 3 minus 32 on 5. And when I sub in 0, I'll get 0. I should have worked this out earlier. 32 on 3 minus 32 on 5. I think that's going to be 64 on 15. I think that should be the right answer. Okay, and then this is the end of part D and the end of question 11.